for welding. No judge. All right, so Z-test using the critical method here. So it says the average 1-year-old, both genders, is 29 inches tall. A random sample of 30 1-year-olds in a large daycare franchise resulted in the following samples of heights. Can it be concluded that the average heights differ from 29 inches at a significant level of 0.5? So again, we're going to assume the standard deviation is 2.61 inches, so we don't have to calculate that. What would our null hypothesis state here? Yes. Something is 29 inches, yeah. So what would you say that null hypothesis states? No, that would be the alternative. So what would be the null? Right? We got that is 29 inches. Okay, so you're saying the mean, the average. Okay. So let's put that in more clarification of rewording the paragraph research into the statement. There it is right there. Perfect. So that's kind of what you need to kind of wrap your head when you're stating the hypothesis and stuff like that. And again, it just goes back to what you learned in English where you're just rewording the question back to you. So the null hypothesis states that the average height of 1-year-olds is 29 inches or something along those lines. Okay. And again, null hypothesis is always going to be the equal to. But what is the alternative hypothesis here? Good. How do we know that by using the wording in the paragraph? Okay, gotcha. The word differ is going to be not equal to. So there's no less than, there's no greater than operations, increase, decrease. But the word differ just simply means not that value, right? So that's going to be a not equals to. So how would you write this then in words? Perfect. Is not. Good. So I'm good with that. So the alternative hypothesis states that the average height of 1-year-olds is not 29 inches, or Elliot, yours is good too, or differs from 29 inches. So anything along that. Any questions here on null and hypothesis or alternative hypothesis from Monday or last week, I guess? All right. I will say for me, when I was a student, this part was my hardest part, just trying to make the correct statements. The math part was always easy, but just those correct paragraph forms is my difficulty. Yes, probably. Yeah. I warned y'all on day one. This is English 5. If you liked math, college algebra would have been the ticket to go. I wish we would have done both. In the next semester, yeah. And the only reason I say that is either A, you can use it as a math credit, or even if you only need one math credit for your degree, that takes care of an elective that you don't have to go take care of. But all right, so now we can get to the part that we're probably more familiar with. The null hypothesis, the mean is what? Equal to 29. And the alternative hypothesis would be not equal to 29. Right? So what is your claim here? Are you claiming the null or are you claiming the alternative? We're claiming the alternative because we're just the researcher is stating that there differs 29. So the claim is the alternative. Right? The null is always going to be equal, but the claim is not always the null or the alternative. Since we're trying to say that it does differ from 29, then we have to go with the alternative. Had that statement said the average height is 29 and we're claiming that, now our claim is the null. All right? Does that make sense on when we claim the null? We only really claim the null if we're ever trying to figure out that, hey, it is this value. Anything other than that, it's usually always going to be the alternative. Good. Cool. All right, so the significant level here was told to us is 0.05. So this test is a what? Two-tailed. And the critical values are what? But remember, 0.05 is a 95% confidence interval. So at 95%, what was our z-score? That would be 99, 1.96. Now, if you forgot that, do remember you can take the 0.05, divide it by 2, and you get 0.025. Look at your Z chart, and you should get the values of negative 1.96 or positive 1.96. Yeah, remember this right here, the critical values is going to be alpha divided by 2, and then this guy is basically your alpha. Right? So either you have it memorized for 95, or you take whatever your significant levels is, which is your alpha, divide it by 2, and then that is your psi. So we're good? Okay. So we're not going to use technology, or are we? So using technology, find the test statistics. Oh, it's wanting us to find the mean. What's the formula? Okay. That's what's asking us to use the technology. Is we have to find out. So it says using technology, find the test statistics. So what the blank here is asking you to go find the mean. And then we can use the standard deviation of 2.61. So let's do that. That shouldn't take us too long, I don't think. It's only 30 babies. All right, so we got 25 plus 32 plus 35 plus 25 plus 30 plus 26.5. Oop. Oh, you're right. Oh, no. We have it. The 29 is the population mean. The sample mean will be what we calculate here. So let's finish where we're at. So 26 plus 26 plus 25.5 plus 29.5 plus 32 plus 30 plus 28.5 plus 30 plus 32 plus 28 plus 31.5 plus 29 plus 30 plus 34 plus 29.5 plus 29 plus 32 plus 27 plus 28 plus 27 plus 32 plus 29.5 plus 33 plus 28 plus 29. Divide that by 30. Did y'all get 29.45? It looks like you're still counting. It looks like to you. Well, I'm completely wrong. So which number did I miss? This kid. I am kidding. All right, so okay, so using technology, now we can find the test statistics, and remember the equation is the sample mean minus the population mean divided by square root of n, or the sample. Perfect. Thank you. So the sample means what we just calculated, which was 29.45. The population mean is 29. Standard deviation was 2.61, and our sample space was 30. All right, so let's figure out what this is. Ooh, this is gonna be hard. So 29.95 minus, nope, 20. Oh, it is 29.45. I thought, oh gosh. So 0.45, right? So that's the top part here. Bottom part's gonna get a little interesting. .61 divided by 30 square root of 30. Okay. Say 4.477. So I got that 5.477. 0.45 divided by 1 point. Yeah, I did mine wrong. Oh, because I did. Sorry, this is what I didn't do. So 2.61 divided by 30. I did the square root, but I forgot to hit enter to get the actual result. So it's 0.4765. So then 0.45 divided by. Sounds good. There you go. I still feel like those numbers were wrong. I bet I could do something like this though. Let's try. Let's do this. Let's do 0.45 divided by, no, 0.45 divided by parentheses 2.61 divided by 30 square root, enter. That looks better. Is that what you got? Okay. So yeah, this could work better than Microsoft, whatever you said on the task bar. Yeah. Oh, it's amazing. I didn't have to do that by hand. Absolutely not. You should use RStudio, which is what I had to use when I took college statistics. And you had to type in codes just for it to add and multiply numbers. I couldn't just say 24 plus 97. I had to go take the sum of the A equal to 24, B equal to 97, and then you go A plus B. But you had to type in the code and then type in the letters and then get the result. And it was the worst. I did that by hand. I did now. It did benefit to come up with like my 5 number summary, do my mean, so I could just type in the data, type in the code, find the average of the X1 column, and then it would spit out the answer. And that was a lot quicker than doing that by hand. But all right, so I don't know what this is, but this right here was 0.944. So now it says compare the critical value and direction to the test statistics in order to make a decision. All right, so here we go. So do what? The negative sign. So okay, I see what you're saying. So the 0.944 is not outside of the negative 1.96. Is that the negative you're talking about? Oh, okay. Because I'm over here going, the negative sign. Okay, I got you. Okay, so y'all's argument is to do what? Why? It's good. It's between negative 1.96 and 1.96, so it's in the non-critical region. So therefore, yes, you're right. I just wanted to make sure y'all got it. So because this right here, 0.944 falls between 1.96 and negative 1.96, then yes, we do not reject the null hypothesis. There's not a significant difference to claim that it could not be. Yes, or negative 1.97 on the flip side. Yeah. So in this one, again, we do not reject the null hypothesis. So again, there's just not enough evidence to say that it will not equal 50 or will not equal 29, right? So let's write that in words to make more sense. So there is or is not. Which one? Okay. If I know where I'm at. All right. Not enough evidence to support the claim that the average number of 1-year-olds what? Not is or is not? Is not 29 inches. All right. So again, there is not enough evidence to support that the claim of the average number of 1-year-olds is not 29. All right. So remember, our claim was that it differs from 29, but because we failed to reject the null, we just don't have enough evidence to state that there is that it could not be 29 inches. All right. Questions on that, and that's with a 95% confidence level. You good with this? On the homework, is it just fill in the blank? Or do you have to write it out? I might do that too. If you writing out a whole paragraph. Less I have to grade. All right. Remember, when the test statistics falls in the critical region, your decision is to reject the null. Indicates that the difference is what? If it falls inside the critical region, indicates that the difference is what? There you go. Yeah. Words that work, right? So when the test statistics falls in the critical region, your decision is to reject the null hypothesis, and it indicates that the difference is not likely to have been due to chance. When the test statistics falls in the non-critical region, the decision is to not reject the null hypothesis, indicates that the difference is likely due to chance. Questions there? That's using the z-score stuff. So let's look at probability testing. No, probability testing, they give you the probability of success and probability of failure versus what we just did, which is mean testing, is you have to find your own average per sample and population, and you find your z-score and stuff like that. All right, so using the p-value method for hypothesis testing, usual levels of significance used to test hypothesis are 0.05, 0.01, and sometimes 0.10. That did not go in order. I know. So this is basically a 95% confidence, 99% confidence, and then sometimes you'll see a 90% confidence. The choice depends of how important it is that we do not make a type 1 error. What's a type 1 error? Correct. And what's a type 2? Very good. What are we saying is false or true? Good. Good guess. That's because it seemed like we're going with this one. Yeah, too easy. All right. Again, we can use of technology has been made finding another statistics called the p-value for the hypothesis testing. So the definition for p-value is the p-value or probability level is the probability of getting a sample statistics such as the sample mean or a more extreme sample statistics in the direction of the alternative hypothesis when the null hypothesis is true. So again, this is just talking about getting the probability that you are going to hit the mean versus the probability of not hitting the mean. So probability of success and probability of failure. In other words, the p-value is the actual area under the standard norm distribution curve or other curve, depending on what the statistical test is used, representing the probability of a particular sample statistics or a more extreme sample statistics occurring if the null hypothesis is true. All right. So it looks like it gives an example, but did it do it for you? Darn it. The next one doesn't. Okay, so let's walk through it. So in this one, example 5, it says decision for a p-value for different significant levels. Suppose a computer printout shows a p-value of 0.0356. So again, that's the probability of landing on the mean. For an alternative hypothesis, let's see. So what is suppose a computer printout shows a p-value of 0.0356. The rest of it says then for alternative hypothesis, they're claiming that the mean would be greater than 50. It says that our sample mean ended up being 52. Our alpha or our significant level is 0.05. It says the null hypothesis will be rejected since the p-value is less than the alpha. So someone did the math, calculated the p to be 0.0356, which is outside of my 0.05. And again, this is a one-tailed test, so we don't have to divide this by 2 and look at it that way. However, if the same hypothesis test is used for an alpha at 0.01, the null hypothesis is not rejected because now it's no longer in the critical region. You now have a larger significant level, right? Because the p-value again is greater than the alpha. So if the hypothesis test is a two-tailed test, this is what I was just saying, the area is one tail must be doubled. For a two-tailed test of alpha at 0.05, you got to look at the 0.0356 for two tails would be twice that, which is at 0.0712. Thus, the null hypothesis will not be rejected because now the p-value is now greater than the alpha. So when we deal with a two-tailed test, we will double the p-value. And if that then falls outside of our confidence level, then we can then say it fails the null hypothesis, or we reject, or not, sorry, failed to reject. Any questions there? All right, so that gives us a little good example to go off of. Those are some weird question marks there. Is that what showed up on y'all's? All right, if y'all wanted to replace that with equals 0.05, and that's a lot of question marks for one little word or number. All right, so decision rule. So if the p-value is less than or equal to the alpha, we reject the null. If it is greater than the alpha, we do not reject the null, or we fail to reject the null. So notice the alpha is chosen by the researcher before the statistical test is conducted, so you don't have to worry about that, while the p-value is then computed after the sample mean or the test statistics has been found. For a z-test, you can easily use a table E in Appendix A to find the p-values or use technology, but we're not using that. We're going to use the table. First, find the area under the standard normal distribution curve corresponding to the z-test value. For a left tail test, use the area given in the table. For a right tail test, used 1 minus that result so you can get to the other side in the table. To find the p-value for a two-tailed test, double the area you found in a one-tailed test. However, calculators and computer softwares that calculate a p-value will calculate the actual p-value, so subtraction and doubling are not needed. But we'll be using our own technology, our own formula, so we'll have to double it. There we go. So procedures for solving hypothesis testing problems using the p-value method. State 1, just like always, we will state the null and alternative hypothesis and identify which one we're claiming. It's either going to be equal to or it's going to be the alternative. Step 2, we're going to compute the statistics test or the test statistics. Step 3, we'll find the p-value if not already given to us. Then step 4, we're going to make the decision to either reject or we do not reject or fail to reject. We do not accept anything. And in step 5, we'll summarize those results in a nice clean sentence. So guidelines for p-values. Again, if p-value is less than 0.01, we will reject the null hypothesis and the difference is highly significant. If the p-value is greater than 0.01, but the p-value is less than 0.05, we will reject the null hypothesis and the difference is just significant. So notice the word there between highly and just significant. If the p-value is greater than 0.05 but less than 0.1, we'll consider the consequences of a type 1 error before rejecting the null hypothesis. Right? So we'll still reject it, but we might say that we have a higher percentage of making a type 1 error. If the p-value is greater than 0.1 period, we will not reject the null hypothesis and the difference is not significant. So we cannot claim that the null hypothesis is basically false. We'll have to say we failed to reject. Any questions there on looking at the p-value and the intervals? So again, notice the word, if it's less than 0.01, we use highly significant. If it is between 0.01 and 0.05, it's just significant. Okay. So let's look at an example. So it says a researcher claims that the yearly consumption of soft drinks per person is more than 52 gallons. In a sample of 50 randomly selected people, the mean of the yearly consumption was 53.7 gallons. The population standard deviation is 3.5 gallons. And we're going to find the p-value for the test. You must use technology or the table on the basis of the p-value in the researcher's. And so the question is, on the basis of the p-value, is the researcher's claim valid? So step 1, the null hypothesis is what? Not for the null. Is, right? The null is always going to be equals because that's what we test. So again, so anything along the lines of the null hypothesis is that the average yearly consumption of soft drinks per person is 52 gallons. And we will denote it as such. Okay, so remember, null is always going to be equal. So now, what would the alternative hypothesis be, which is the researchers claiming what? Greater than. Any one of those words, greater than, more than, increase, anything along those lines. So the alternative hypothesis, which again is the researcher claims, is that the average yearly consumption of soft drinks, so always stating the situation first, per person they used is more than, but I would accept greater than, increased by, or whatever, is more than 52 gallons. And we will denote this as H1, where the population is greater than 52. What type of test this will be then? Well, it is a one-tail. What type of one-tail? All right, very good, because we're going to look at the right side of the graph because we're looking at things that are greater than 52. All right, so the test statistics for the z-test is as follow. The sample mean given to us was 53.7. The population mean was 52. We're going to divide that by the standard deviation of 3.5, divided by the square root of the sample space, which was 50. So let's figure out what that is. So we got 53.7 minus 52. Get 1.7. We're going to divide that, use parentheses, and we're going to say 3.5 divided by 50. But we're going to take the square root of that result, close parentheses, hit enter. Is that what y'all got? I hit it after. So in this case, I would have got a pin. 3.43. All right, so that's what our z-test is stating to us. All right, so has everyone got that down? I want to scroll up. Okay, so I'll rewrite it here real quick. It was 3 point what? 43. All right. So the p-value so 3.43 is what we got. So the p-value, we would have to use the table E. What is the z-score at 3.43? What's the area under the curve? Okay, 0.9997. But because it's a right tail test, what am I going to have to do with that score? So do 1 minus that, and we get. All right, cool. All right, so our p-value then is 0.0003 from the table E. The p-value found using technology or our table E. I guess if you were using technology, it would still be 0.003. I don't know why they added that in. So what is the decision? What are we doing? It's 0.0003. What are we doing with that null hypothesis? Do it. Go back to what our saying was. At a p-value of less than 0.01, what are we doing? Go back to the guidelines for the p-value. We are rejecting this null, right? Because we have a highly significant level. The decision is to reject the null hypothesis, and there is sufficient evidence, or really, there is a high significant evidence to what? How would you write this out? Correct. We know we're rejecting it, but how would you write out this? If we're rejecting the null, that must mean that we're accepting the what? The alternative, and the alternative is the what? Correct, but it's whose alternative? The researcher. So therefore, are we accepting or denying our claim? There we go. All right. So there is a sufficient evidence to support or accept the researcher's claim. And then this is where you then can restate the question. So we support the researcher's claim that the yearly consumption of soft drinks is more than 52 gallons. So the test, again, I guess that's the same thing. The test supports the decision that the researcher's claim is valid. I think I would probably accept the word accept as well. That seems like those two are the same. Any questions on that then? All right. So that is the conclusion of 8.2. So you should be able to now finish up that homework. Let's get into 8.3, which I think is pretty short. So if I can't finish it today, I'll definitely be able to finish tomorrow. But it is the t-test for a mean. So the objective 6 here is to test means when a population standard deviation is unknown, and we're going to use the t-test to do that. This is where you have the degree of freedom and all that stuff that we did at the end of chapter 7. So more often than not, the standard deviation of a population is unknown. So this is more a realistic type of situation you'll deal with in the real world if you do become a statistician. So the z-test is not typically used for testing hypotheses involving means. The t-test is used instead. The distribution of the variable should be approximately normal. And properties of this t-distribution, similar to the standard normal distribution, is as follows. The t-distribution is bell-shaped. Very good. The t-distribution is symmetric about the mean. And the mean, median, mode are equal to 0 and are located at the center of the distribution. And the curve approaches but never touches the x-axis. I feel like we've written these notes out before. So properties of the t-distribution that differ from standard normal distribution are as follows. The standard deviation is greater than 1. Very good. The t-distribution is a family of curves based on degrees of freedom, which is related to sample size, because remember, degree of freedom is just n minus 1. So as the sample size increases, the t-distribution approaches the standard normal distribution. And so the larger our sample size, the closer we get to that. We still good? All right. So in our definition here, it says the t-test is a statistical test for the mean of a population and is used when the population is normally or approximately normally distributed and the population standard deviation is unknown. The formula is as follows. You can kind of see it's pretty much the same. The only difference is we're going to use a sample standard deviation, which is what this lowercase s is. That's the only difference from a z-test. And again, reminder that the degree of freedom is n-1. So we'll use table F to find critical values for the t-test. Remember, degree of freedom's larger than 30. We round down to the nearest table for conservative approaches. So I think on your chart, it goes 30, 40, 50. So anything between 30 and 40 will go to 30. Anything between 40 and 50 will go to 40. Anything greater than 50 will just go to 50. All right. So as degree of freedoms get larger, the critical values for t-test approach the z values. So assumption for t-test for a mean when population deviation is unknown, we have to assume the sample is random. And then either n is greater than 30 or the population is normally distributed when n is less than 30. And then we use those degree of freedoms in the table F chart. The procedures for the t-test by the traditional method is, just as always, state the null and alternative hypothesis and identify what you're claiming. Are you thinking it's equal to, or is it the alternative for either less than, greater than, or not equal to? Step 2, find the critical values using our table F. Step 3, we are going to compute the test statistics. Very good. Step 4, again, we will make a decision to either reject or not to reject the null hypothesis. And then our step 5, summarize the results by restating the researcher's claim into your response. And just like in the z-test, the t-test for p-value methods are also pretty similar. We will still state the null and alternative hypothesis and identify the claim. Step 2, again, we will compute the test statistic. Step 3, this time we'll find the p-value. And that's what we then use that chart to determine where we will reject the null and how confident are we with that. Step 4, we'll make the decision again to either reject or not to reject the null hypothesis, and as always, summarize the results, restating what the researcher was claiming. Any questions here? Okay, let's do an actual problem. I went through those notes pretty fast there. Seems to be the same process every time. So example 7 says, using table F, we're going to find the p-value intervals for each test value. So if I get t equals 2.321, n equals 15, and it is right-tailed. Right, so let's go down to the solutions here. This is your table as well. I have it on my paper, so I'm going to trust that you can use it on yours. But to fill out these answers, it says in table F, we're going to choose the row degree freedom, which again is n-1. We're told that n is equal to 15 in that first question. So the degree of freedom would then be what? 14. So we'll go to that row that has 14. And then we are looking for a probability, not probability, sorry. What's this stuff? The area under the curve with a t-score of 2.321. So at 14, 2341 is going to be between what two values? Good. We are also told that it's a right-tailed. So is that a 1 or 2-tailed test? So let's look at those numbers there. Ooh, one tail, one step above that. There it is. So we'll use the values of 0.025 and 0.01, right? Somewhere between that is where our significant level will cross. So the one-tailed area above these values. Oh, I wrote that in the wrong spot. Sorry. That goes here. Those numbers will go there. So this would be the 2.145 and the 2.624. Right? And then these are the one-tailed areas above. Therefore, the p-value that we would calculate has to be between 0.025 and 0.01. So the p-value obtained using a computer calculator is what? So let's calculate that. That would be, so remember to find this, it would be, is it population mean? No, sample mean first, right? All right, so sample mean, oh, we don't even have a sample mean. So, okay, but that would be that. So then we would need to go back to the table E and look at what the z-score or the area under the curve at 2.321. So if they're giving us this result here. So now we got to go to table E, look for the z-score of 2.321 to find out what is the area under the curve. At 2.3, it should be negative. No, this is the z-score. So basically, remember the t-score gets as close to the z-score as it can, because again, you're less than 30 right now. There you go. Okay. So we get the area of the curve, which is 0.9898, but it's a right tail test. So therefore, what do we do with this? We'll do 1 minus 0.9898. And what's that give me? Yeah, I think you're right. Good. So we didn't have a calculator. We used our table and we got 0.0102, which again, does that fall between 0.025 and 0.01? Oh gosh, because I wrote it the wrong order. 0.01 is definitely smaller than 0.025. That's my fault. Let me re-ask the question again. Does that fall between those two values this time? So always make sure your teacher is putting in the correct numbers there. You gotta stay on top of him. So questions on that. So this information was given to us. We're just kind of comparing it. Charlie, you got questions? Cool. All right. So in the second example, it says table F, choose the row of degree freedom. This time it was told to us that we had 24. So the degree of freedom would be 23, which it states there. So I'm going to go to my 23. And we have a t-score of negative 1.415. Not gonna pay attention too much of the negative, but that definitely looks like that would fall between 1 point. Well, no, well, we're gonna look at where it's between right now. So that's gonna be the 1.319 and the 1.714. And then we'll continue this discussion tomorrow. Finish it up, and you should be able to finish up homework. Yeah, because we're literally on the last problem.